In today's video, we're going to look at dilations and reflections of parent function graphs. So we're going to be looking at more transformations. Last time we looked at specifically translations, where we were just moving our graphs left, right, up, down, and we were looking at what happens when we plug in an H value or a K value. So don't forget your resultant equation. So when your final equation is done, anything is simplified out. If you see something like inside a grouping symbol like x minus 2, that really means you're moving to the right from your original parent function. Whereas if you see that k value, like a minus 5 tacked on the end of your formula, that really means you're going to move the whole graph down 5 units from what your original parent function would look like. So what we're looking at today, again, dilations and reflections. So these should sound familiar from geometry. Again, your dilation is when you have any kind of change of size. So that could be a stretching or a shrinking, or you might call it expanding or compressing. And we also have reflections, in other words, a flip over a mirror line. So our reflections that we're going to look at are going to be reflecting either over the x-axis or the y-axis, although as you go on in math, you might be reflecting over other lines. And in fact, actually later on during the course, we'll see what happens, what our implications are when we try to reflect things over the line y equals x. But right now we're just going to do horizontal or vertical reflections and horizontal or vertical dilations that can change our graphs. And these are the final transformations that we need to look at. And then we'll see an example where we start putting these ideas together. So for our first transformation, we're going to look at the square root or the radical function. And so we need to make sure we keep in mind what our original function looks like. So we had our critical points, one at 0, 0. We had another point at 1, 1. And I can actually graph another one with this. Our next number that we can take a perfect square root of, well, we can take the square root of 4, and the square root of 4 is 2. And again, this was the function that kind of just started at the origin and then went up to the right. We don't have any values in here in the negative, either in the x or the y, if we're just talking about our basic parent function. But that's when we have no modifications to the equation. So what happens when we start changing it? So our first one, we're going to change it so a equals -1. So a, you'll notice in your transformation form, that's the variable that's right out in front of the function. So we're looking at this spot right here. So if we put a -1 in that spot, aka multiplying by a -1, that's this negative that we have out in front of the square root. So let's think about that for a second. If it's outside of the square root, that means whatever we're plugging into the function, we're going to take the square root of first, and then we're going to multiply it by a -1. So all of our answers, in other words, all of our outputs or our range is multiplied by a -1. So for example, let's use some of the points that we have in our original parent function. So we have a point 1, 1, which means when you take the square root of 1, you get out the answer 1. Okay, well, what's going to happen if we multiply that by a -1? Well, 1 times -1 is -1. And so when I plug that function in, we have 1 is our x that we plugged in, but when we multiply that by a -1, we actually go down instead of up. And same thing with our next point. If you take the square root of 4, your answer would be 2, but then when you multiply that by the -1, you get a -2. Why do you think I skipped over 0, 0? So what happens when you multiply 0 by a -1? Absolutely nothing. So actually our 0, 0, our origin point, didn't even move. So it looks like, compared to our original graph, we actually flipped our graph over the x-axis. We made a vertical reflection or vertical flip. So if the numbers on the outside of the function always do something vertically, what do the numbers inside the function always do? So just like with the h and the k, when we throw something inside the function, we're dealing with a horizontal. So if we think of this in terms of, well, how are we plugging numbers into this function? If you plug in a number, say like 1. Well, wait a second. We have to think of taking that negative value. We can't do that. What's the square root of -1? Doesn't work. But what if we plugged in a -1 to start with? So if I plug in a -1 as my x, well, -1 times -1 is 1. Now I can take the square root of that. I can do that with 4 as well. So if I plugged in a -4, but multiplied it by a negative, now I've got square root of +4, which is 2. Again, 0, no changes. So even when we multiply it by a negative, we still have 0, and the square root of 0 is 0. So with this one, again, just even looking at the numbers in that function, we've actually flipped this over the y-axis, or we've done a horizontal flip. So to kind of combine these ideas together, to summarize, if we're looking at a vertical reflection, the first one that we did, then we're basically flipping over the x-axis, and we're changing that a value. So any number out front, if it's negative, it is going to flip up to down or down to up, wherever you started on your parent function. We also have a horizontal reflection. And so that's the second one that we did. And that's when we put that b value was -1, where we multiplied by a negative on the inside. And that's going to flip horizontally, AKA it's going to flip over the y-axis. And so if you want to, this would be a good time to pause and actually go out to Desmos and plug in these two functions. So see what happens when you plug in the function y equals -x². We would expect the graph to be going up. But if we do a vertical reflection and everything flips down, that would make our parabola face downward. Or if we do this with a cube function. So again, we've got, excuse me, I'm backwards on my video. So we have our function that kind of looks like this. And so if we flip that around horizontally, again, we're changing where the branches are. So again, this would be a good time to kind of pause and then go back to desmos.com/calculator, or go to the link that I'll have on here that you can play around with, and see what happens. So those are our vertical and horizontal reflections, but we still have to look at dilation. So again, dilation is a change of size. So we're either going to be stretching or shrinking, either in the vertical direction or horizontal direction. And again, most of the problems that you're going to see this year in Algebra 2, actually just about all of them, we're really just going to be focusing on the the vertical stretching. But I want to show you what happens when the horizontal gets in the mix as well. Okay, here we go. So again, we're going to do this with our absolute value function. So again, same as the square root function, we had our main critical point 0, 0. And we go up 1 over 1. Because again, if you think about how you're plugging into the function, what's the absolute value of +1? Well, it's just 1. What's the absolute value of +2? It's just 2. But then when we go in the negative, what's the absolute value of -1? Well, that's 1. Or the absolute value of -2. And so we have a very distinct, sorry, let me clean that up a little bit. We have a very distinct V shape, but we have a perfect slope of +1 on the right and -1 on the left. Okay, so let's throw an a value in there, but now let's use a value that's different from 1. Let's use 2. So again, if we're on the outside of the function, we're basically taking the answer to that function, our range, and we're multiplying those values by our a value. So if I take all of my y values and multiply them by 2, those are the new points I'm going to want to use. And again, if I plug in 0, 0, well, I'm getting 0 out as my y. 0 times 2 is just 0. So that doesn't help me out. But when I look at my next point, 1, 1, my y value is 1. Well, 1 times 2 is 2. My next one, my original point was at 2, 2. So I take that answer, the y equals 2, multiply that by 2, and I'm actually at 4. And exactly the same thing happens, just in the negative on the left-hand side of the graph. And again, perfect V shape. Again, sorry, I'm not using a ruler, so my lines aren't perfect, but that's why I draw my points in there. So even if my line or my sketch isn't perfect, you know exactly which points I'm going through. So with the 2 out front, be careful. I don't want you to think of this in terms of a horizontal movement. We want to think of this in terms of a vertical movement because we're using that A value, and everything outside our function, outside the grouping, is always going to be a vertical change of some sort. And so if you think about it, since I was multiplying my Y values and moving all my Y values up, an easy way to think of this is I stretched it by 2 times as tall. So I hung on, if you think of hanging onto that bottom point, origin, or the origin point, 0, 0, keeping that exactly where it is, and then holding on to the ends of your V and stretching them up, it's going to pull all those points so they're a little taller. Yes, it looks like it's skinnier, but think more in terms of what's changing on the Y values. Our B value that we're going to try out is 1/2. So again, keep in mind, we almost have to think of these horizontal, these inside values inside the parentheses, almost backwards from what we think. So usually when you see the number 1/2, you would think, oh, it's going to be half as big. But that's not really the case. So if we think about how we talked about shifting things horizontally last time, we basically had to take the point from that original X value we would have been plugging in, and then we multiply it by that number. So my original point, 0, 0, well, if I multiply that by 1/2, nothing happens. My original point, 1, 1, I'm plugging the 1 value in for the X. So I really want to look at, well, what's my value at 1/2 instead? Well, it's only going to be going up half as much. So over 1, I'm actually only going up half the value. And it's the same thing, exactly perfectly reflected in the Y-axis, just because that's the nature of this V. And so let's think about it with the next point. So again, if I was to plug in 2, we really want to use what would have been the Y coordinate on our original function at X equals 1, which would have been the point 1. Same thing's happening on the other side. And so just like when we were talking about translations, where we'd have to do the opposite of what we think. If we're thinking of terms of dilation or stretch and shrink in the horizontal, we would think 1/2 would mean shrink it in towards the center. It really doesn't. 1/2 really means stretch it out from the center. And again, if you don't believe me, one of the best things to do is actually go back and try out that Desmos activity. And so there's going to be a link to it right below this after we look at our last example that you can check out. And again, there's a slider in each one of them, and you can play around with those to your heart's content. So you can see what happens when you change those values, positive and negative, and where it ends up moving those graphs, how it ends up changing your stretches or your shrinks or what have you. But just to summarize what we're looking at, we did, again, vertical and horizontal. And we actually talked about 2 things. We had some positive numbers and we had some negative numbers, and we have to put some fractions into the mix. So our most general description is, if we're looking at a vertical dilation, and again, we're looking at what happens when we plug a number in for that A value. 2 things. So we looked at, again, this very last one, we put a 2 out in front and it stretched it up. So if we did a fraction, if we did something smaller, it's actually going to compress it down. So when A is greater than 1, like 2, 3, 4, 5, we're going to essentially stretch everything by a factor of that A. But if we're looking at a number between 0 and 1, we're looking at a fraction. Again, it's going to go along with our gut, with our, with our thought of, hey, these numbers are supposed to make stuff smaller. So it's basically going to do a shrink by that factor. You can also think too in geometry, when you were doing dilations, you're really just multiplying, and that's the same way I came up with the points that I wanted to graph. Okay, we also have a horizontal dilation. And again, these go opposite from what you think. So when we plugged the 1/2 in, so when our number was between 0 and 1, that actually looked like a stretch by that factor of b, although technically we need to update that, and I'll update this then in the copy that I post. So we're stretching kind of by a factor of that reciprocal. So when we had 1/2, or rather that should be a 1/b. So when we had 1/2, we actually made it look like it almost stretched by a factor of 2. It was twice as wide. So when b is greater than 1, it's going to go opposite from what we think. So that's the one that's going to look like the shrink. And it's not really a factor of b, it's really 1/b. So if we had a 2 inside the grouping, so like inside the absolute value bars, it would look like we shrink it to half the size. Okay, so let's put these ideas together and look at a few different transformations in the same graph. So again, as I mentioned, you're really only going to be worried about the vertical dilations and then the vertical and horizontal reflections. We're not worried so much about the horizontal dilations, and actually you won't see the horizontal reflections all that much, but those are more likely to pop up. Okay, so our final example. So we're going to describe the transformations from y equals x cubed and graph it to the right. And the new function we're going to do is y equals -3 times x plus 1 cubed plus 4. So the first thing I'm going to do is actually graph my original function. I want to know where I'm starting from. So let's put that one in red. So our cubic function, again, it had a point at 0, 0, 1, 1. And then if we think, well, what happens when we cube 2? Well, 2 cubed is 8, so 1, 2, 3, 4, 5, 6, 7, 8. And same thing in the completely opposite direction. 1, 2, 3, 4, 5, 6, 7, 8. So here's our original parent function. And it's never a bad idea to sketch out your original. So that's y equals x cubed. And so now let's look at what happens when we perform each one of the transformations that they're talking about. So again, I like to divide it up. So first thing is, I look at the h and the k values, because that tells me where that origin point, where our main critical point is going to move. So +1 inside the function, what does that do again? Okay, that's going to actually move things to the left one. Okay. So that's going to go left 1. But then the k value of +4, if he's moving vertical and we go with our gut, with our instinct, it's actually going to move it up 4. So our initial point, our 0, 0 point, actually moves left 1 and up 4. Okay, then our next thing though is we need to multiply everything by a -3. So actually, let's do this. So first thing I'm going to do is let's graph this without that change. So if we were to graph just y equals x plus 1 cubed plus 4. Again, all I've done is shifted things over. Here's where that graph is going to go. So this is, again, the purple graph. So now we have to address the last piece of this. So we need to look at this -3. How about we not cover that up though? So this -3 again out in front means we need to take everything and multiply it by -3. So that's actually going to do two things. So the negative, if it's outside the graph, which way is it going to flip? We're going to flip vertically, because again, we're outside the graph. And then the 3, because it's bigger than 1, is actually going to stretch everything. So our final equation is going to, let's see, if we do that to our original point, nothing happens. Again, we originally plugged in 0, 0. When we multiply by a negative, nothing happens to it. So our initial point doesn't actually move anymore. everything else still needs to get multiplied. So we have this point sitting at 1, 5. It's going over 1, up 1. Instead, it needs to go over 1 and down 3 for that -3. Same thing, this guy to the left. He went over 1, down 1. So we need to, instead of going down 1, go up 3. 1, 2, 3. So our new graph, y equals -3, x plus 1 cubed plus 4. So I'm actually going to erase my purple kind of intermediate graph so we can see our kind of answer more clearly. So let's get my eraser tool going. There we go. So there is our final graph with all of our transformations applied. Again, play around with that Desmos activity. We're not actually going to do a lesson check today. You're going to come back and do the group activity, the last part of class, and you'll have these problems included in your lesson check for next lesson. But definitely do check out that interactive exploration on Desmos. Again, I'll post the link again in this lesson so you don't have to go looking through Schoology. So check that out, as well as the extra required activity that I have posted. Again, just a quick little 5-question, play around with it, and then come back to our class and we'll do our activity, which will be our finish for the day. Alrighty, see you in a little bit.